Literal values in Verilog are a little bit more complicated than declaring a constant value in another language such as C. So input 7 of our mux here has the constant value 42. But why don't we just write 42? We've got all this extra stuff. The reason for this is that values in Verilog can be represented by any number of bits. So when we're declaring a literal, we also need to declare how many bits we want to use to represent that literal. The general structure for declaring a literal is the width of the literal value in bits, then an apostrophe, then the format of the literal value, such as hex or decimal, and finally the actual value itself. The width of the literal value can be any positive integer we like. That is one of the beauties of developing hardware. We can make architectures that have 7-bit data paths, or 16, or 32, or 1050. The format is then typically either a decimal, which is a D, a hexadecimal, which is a H, octal, which is an O, or binary, which is a B. Let's do some examples. Say we want to assign the output Q, which is a 16-bit signal, with the decimal value 42. In our procedural assignment block, we would write Q equals 16 for the number of bits that we want our literal value to be, apostrophe D, because we're writing a decimal, 42 for the actual value itself. Then we can make this and run it, and we can see that in the simulation output, the output of Q is always 42. Let's do the same thing but in hex. So we can write Q equals 16 apostrophe H. So we've changed the D to a H, and then we write the value itself in hexadecimal. So we write 2A. 2A is 42 in hex, so when we make and compile the simulation, we get the same output. Let's try assigning the value 3 in binary now. Q equals 16 apostrophe B, then a whole bunch of zeros, and then 1, 1. Let's see. Yep, that's 3. Okay. Now let's try assigning a literal that's smaller than 16 bits. So let's change this to be Q equals 8 apostrophe D 100. Now here we can see that the compiler is complaining because the bit widths don't match. One thing that we can do to fix this is to use something called concatenation. Concatenation is essentially where we can stitch different signals together to make up a bigger signal. So we can stitch together 2 smaller signals to make up the full 16 bits of Q, let's say. To perform concatenation, we use some curly brackets to contain a list of all the signals that we want to stitch together. Each signal in the list is separated by a comma, and they're put in the order of the most significant bits to the least significant bits. So let's say we have the first 8 bits be a literal with the value 0, and the second 8 bits be a literal with the value 100. Now that works. We've created a 16-bit number out of 2 8-bit numbers. We can of course do this with other signals also, not just literals, but we'll look into that a little bit later. Okay, that's the end of video 2 for this lesson. Now you can look at the final video where we look at case statements and complete our multiplexer circuit.